Welcome to another video of first principle. In today's video, we are going to work on a trigonometry problem as shown here. We want to prove the product of half angle cosines to infinity is equal to sine of alpha divided by alpha for alpha not equal to 0. If you have not seen this problem before, you can spend some time on it before coming back to see the rest of the video. And as a hint, I can give you a little bit of clue. First, prove that the multiplication of the cosine half angles up to the power of n cosine alpha divided by 2 to the power of n is this relationship for alpha not equal to k pi. K can be 0, 1, 2, 3, etc. You can now pause the video and come back when ready. Okay, the first step, I would like to prove this identity, which is on the left hand side, cosine of half angles all the way to the power of n is equal to the right hand side. So if I start from the left hand side and multiply it by 2 to the power of n times sine of alpha divided by 2 to the power of n, which is simply the denominator of right hand side, I should show that this is equal to sine of alpha. If I show that, it is same as the lemma identity in the top. Okay, now let's do a little bit of regrouping of this left hand side. What I do, I bring one of the 2's from 2 to the power of n inside a parenthesis and bring the term cosine of alpha divided by 2 to the power of n and the last term sine of alpha divided by 2 to the power of n. Now if you look closely into what we have in this parenthesis, it resembles a formula for sine double angle. If you recall, sine of 2 theta is equal to 2 times sine of theta cosine theta. Now if I put theta equal to alpha divided by 2 to the power of n, 2 times that is alpha divided by 2 to the power of n minus 1. Give you a moment to ponder on this relation and make sure that it is correct indeed. Okay, so now the term that is shown in the yellow color in the parentheses can be simplified as sine of alpha divided by 2 to the power of n minus 1. So as the next step, I bring another term, cosine alpha divided by 2 to the power of n minus 1 into the parentheses and borrow another 2 from previous 2 to the power of n minus 1, which changes the coefficients in the front of this multiplications to 2 to the power of n minus 2. And we can continue this process. The next one will be 2 to the power of n minus 3 times all the terms all the way to alpha divided by 2 to the power of n minus 3 and what we have in this parenthesis. And if you continue this process all the way to n equal to 4, the final coefficients will be 2 times cosine alpha divided by 2 sine alpha divided by 2, which is simply sine alpha. So I prove that the left hand side is equal to sine alpha, so it is equivalence of proving the identity that I was supposed to prove in the lemma. So that is end of the proof for the lemma. Okay, now let's go back to the original identity that I wanted to prove. The multiplication of the cosine half angles all the way to infinity, I wanted to prove that is equal to sine of alpha divided by alpha. So let's start from the left hand side. The left hand side is simply the limit of the cosine half angles all the way to 2 to power of n when n is equal to infinity. Now the argument inside the parentheses I have already shown that is equal to what is in this green color. Call this equation 1. So I really have to calculate this limit now. Okay, how do I calculate this limit? What I do is first bring out the sine alpha term, because it is not dependent on n, outside this limit. So what I will be left is sine alpha times this limit. Now look at inside of this limit. In the sine I have the argument alpha divided by 2 to power of n. But in the numerator I have 1 divided by 2 to power of n. So what I do, I multiply numerator and denominator by alpha. So I get sine alpha divided by alpha because I can bring alpha out of the limit. Now I have alpha divided by 2 to power of n in the numerators and also the argument for the sine. Now let's look at the limits for x divided by sine of x when x is equal to 0 as a side note. And in a moment you will understand why I want to calculate this. But first, let's look at these limits. I cannot directly calculate this limit because if I put x equal to 0, the numerators become 0, sine of 0 will become 0, so 0 over 0 is undefined. So I cannot calculate this limit directly. But I can use the L'Hopital rule by simply calculating the derivative of the numerators and the derivative of denominators when x equal to 0, or goes that as a limit to 0, which ends up being like 1 divided by cosine of x. Cosine of 0 is 1 and the total limit will be 1. Now let's do a change of variable going back to this equation 2 and define x as alpha divided by 2 to power of n. Now what happens if n goes to infinity? Remember that here I wanted to calculate this limit when n was equal going to the infinity. Now if n goes to infinity, alpha divided by 2 to power of n goes to 0, because 2 to power of infinity is infinity, but alpha divided by infinity is equal to 0, goes as a limit to 0. So is x equal to 0. So really the equation 2, what I have is sine alpha divided by alpha, and this limit alpha divided by 2 to power of n, I can use the limit that I proved to be sine of x divided by sine of x, as limit when the x goes to 0 is equal to 1. So this whole limit will be 1 and the final result will be sine of alpha divided by alpha. So I started from the left hand side and proved that the left hand side is equal to sine alpha divided by alpha. And that ends the proof. I hope you found this video helpful. You can subscribe to this channel for future videos. You can leave comments and let me know how you solved this problem. You use the same approach or any other comments and suggestions that you have. Thank you.